Hey everybody! In this section and in this chapter, we're going to be learning about hypothesis tests regarding a parameter. So we're going to start with just the language of hypothesis testing, kind of giving a background here. So let's start with an example. A friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If it comes up tails, they win. Suppose the outcome of 5 plays of the game is 5 tails. Is your friend cheating? So we will determine the probability of getting 5 tails in a row, assuming that the coin is fair. The flips of the coin are independent. So the probability of 5 tails in a row, another way to write that, is probability of t and t and t and t and t. And so remember how this works. We've done this in the past. That's the probability of each individual tail times the next. Okay, and out of every coin flip, tail is 1 out of the 2 possibilities. So the probability of flipping a tail out of the flip is 1 out of 2. And so we just multiply 1/2 5 times, or 1/2 to the 5th power, which gives us 0.03125, or about 3%. So if we flip the fair coin 5 times, 100 different times, we would expect about 3 out of the 100 experiments to result in all tails. Okay, so with that information, so we observe what's possible, but not likely. It's possible that your friend can get 5 tails in a row, but it's not very common or likely. It's pretty unusual. So you can make one of 2 conclusions. One, you could say your friend is not cheating and just happens to be lucky. 2, you could say your friend is not using a fair coin. That's the probability of obtaining a tail on one flip being greater than 1/2, and they're cheating. So these are the 2 outcomes that you can conclude. So is your friend cheating, or did you just happen to experience an unusual result from a fair coin? And so this example is at the heart of hypothesis testing. We can make an assumption about reality. In this case, the probability of obtaining a tail when we flip is 1 out of 2. And then we look at or gather sample evidence to determine whether it contradicts our assumption. So we can't technically prove that our friend is cheating, but we can say whether or not our sample data supports that they are cheating. So what we want to start with here is to determine the null and alternative hypotheses. So let's start with what a hypothesis is. It's just a statement regarding a characteristic of one or more populations. It actually comes from the Greek word that means to suppose. And so in this chapter, we look at hypotheses regarding a single population parameter. And so hypothesis testing is a procedure. So we have a hypothesis, and then when we're doing hypothesis testing, that's a procedure or method based on sample evidence and probability. And that's going to be used to test statements regarding a characteristic of one or more populations. Okay, so here's our steps in hypothesis testing. Number 1, make a statement regarding the nature of the population. That's going to be your hypothesis. Then number 2 would be to collect evidence, which is going to be your sample data, so that you can test your statement. And then number 3, analyze the data to assess the plausibility or likelihood of the statement. All right, so now we have something called the null hypothesis, which is going to be denoted H0 as a little subscript of 0, and it's a statement to be tested. The null hypothesis is basically a statement of no change, no effect, no difference, and is assumed true until evidence indicates otherwise. This differs from the alternative hypothesis, denoted H1, which is a statement that we are trying to find evidence to support. Okay, so another way to say this is that the null hypothesis is a statement of status quo or no difference, and status quo is just Latin for the existing state or condition. So the null hypothesis is going to be the default. It's assumed to be true until we have evidence that contradicts it. And so what we actually are looking for is evidence that supports the statement of the alternative hypothesis. So just think of null as like the default hypothesis. So in this chapter, there's actually going to be 3 ways to set up the null and alternative hypotheses. So here's the 3 ways. Number one is called equal hypothesis versus not equal hypothesis, also called two-tailed test. And so we have our H0, our null hypothesis, where the parameter equals some value. And then our alternative hypothesis, H1, is just saying that no, that parameter doesn't equal that value. Okay, so just with some numbers for you, let's say the probability of flipping tails by default is 1 out of 2, and our hypothesis might be no, it's not true. It's not 1 out of 2. It's something different. So number 2 here is equal versus less than, which is called the left-tailed test. And so H0 is going to be the same. The parameter equals some value. And so our H1, our alternative hypothesis, just says that no, our parameter is actually less than that value. And then very similar, our equal versus greater than, our right-tailed test, we're saying the parameter is actually greater than some value. And so our left and right-tailed tests are often called one-tailed tests. And so just a quick thing to notice, in the left-tailed test, the direction of the inequality symbol is pointing left, so the pointy side of the symbol points left. That's one way to remember that that's the left-tailed test. And then for the right-tailed test, we say that this inequality symbol is pointing right. And then all three tests, the null hypothesis has an equal sign. Okay, so let's see if this makes sense with an example. Determine what the null and alternative hypotheses are. So state whether the test is two-tailed, left-tailed, or right-tailed. So part A, the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. All right, so think about what the null hypothesis is here. It's like the default one. So it's this statement here, 2% of the children have headaches as a side effect. And then the researcher wants to know if the headaches is actually more than 2%. And so the hypothesis deals with our population proportion P. If the new drug is no different from competing drugs, the proportion of individuals taking it who experience headaches will be exactly equal to the 2%, 0.02. And this is because the statement, it's a statement of no effect, no change. So we want to determine if the proportion of individuals who experience a headache is actually more than this number, more than 0.02. And so this is actually the statement we're attempting to find evidence to support. That's our alternative hypothesis. So our null hypothesis is H0 is P equals the 0.02. So the proportion of individuals taking the new drug who experience headaches is exactly 0.02, 2%. And so our alternative hypothesis by the researcher, proposed by the researcher, is H1, that P is actually greater than 0.02, or in words, the proportion of individuals taking the new drug who experience headaches is more than 2%. Okay, so this is a right-tailed test because the alternative hypothesis, we're proposing that it's more than our parameter from our null hypothesis. Or another way to see that is that our inequality symbol is pointing to the right. All right, let's try another one. The Blue Book price of a used 3-year-old Chevy Corvette is $59,083. Grant wonders if the mean price of a used 3-year-old Chevy Corvette in the Miami metropolitan area is different from this number. Okay, so think about it. The hypothesis deals with your population mean, mu. If the mean price of the car in Miami is no different from the Blue Book price, then that's your null hypothesis. Okay, so this is a statement of no difference. And then Grant wants to know if the mean price is different from that amount. So that's the alternative hypothesis. That's the statement we're trying to find evidence to support. So in this case, null hypothesis is mu equals the $59,083. And then the alternative hypothesis is that mu does not equal the $59,083. It could be more or less. It's just not equal to that value. And so this is a two-tailed test because the alternative hypothesis has a not equal symbol. It doesn't have your inequality symbol pointing left or right, greater than or less than, and so that makes it a two-tailed test when it has just a not equal sign. Okay, let's try this one. The standard deviation of the contents of a 64-ounce bottle of detergent using an old filling machine is 0.23 ounce. The manufacturer wants to know if a new filling machine has less variability. Okay, so the hypothesis here deals with population standard deviation, sigma. If the new machine is no different from the old machine, then the standard deviation of the amount in the bottles filled by the new machine will also be 0.23 ounces. So this is our null statement, because it's a statement of no change, that even with a new machine, the standard deviation is going to be 0.23 of an ounce. The company wants to know if the new machine has less variability than the old machine. Okay, so that's the statement we're trying to prove or have supportive evidence for, and that's our alternative hypothesis. So our null hypothesis is that sigma is equal to 0.23 ounce, and then our alternative hypothesis is that sigma is actually less than this, less variability, less change than this. So sigma is less than 0.23 ounces, and then that's going to give us a left-tailed test because our parameter is less than our null hypothesis parameter value, or another way to think of it is because our inequality symbol is pointing left. All right, next let's explain type 1 and type 2 errors. So there's 4 outcomes from hypothesis testing. Okay, so 4 outcomes. Here's number 1. We reject the null hypothesis when we find out that the alternative hypothesis is true. We would say that this would be a correct decision. Option 2, we don't reject the null hypothesis when we conclude that the null hypothesis is true. This would also be a correct decision. Number 3 is our first error, and that's when we reject the null hypothesis when the null hypothesis was actually true. So this would be considered incorrect, and we call this a type 1 error. And then number 4, we don't reject the null hypothesis even though we figured out the alternative hypothesis is true. This would also be incorrect, and we call this a type 2 error. So here's a table for you to just see the overlap of these situations. So in reality, this says that the null hypothesis is true, and our conclusion was that we don't reject it. So this would be correct. Also correct would be if our alternative hypothesis is true, and so therefore we reject the null hypothesis. But we have errors when the null hypothesis is true, but we decide to reject it. That's type 1. And then we also have an error when the alternative hypothesis is true, but we don't reject the null hypothesis. Okay? So hopefully logically this kind of makes sense to you. Don't worry all that much about null and alternative and H0 and H1. Just think about if something's true, we don't want to reject it. That would be correct. If something's alternative is true, something different is true, then we have to reject the opposite of it, the alternative, which is the null in this case. Okay? So let's see if it'll make more sense also with an example. The pharmaceutical company has just developed a new antibiotic. We looked at this one. 2% of the children taking competing antibiotics experience headaches as a side effect. And then the researcher from the FDA wants to know if the percentage of children taking the new antibiotic who experienced headaches is more than 2%. So we've looked at this one. So remember, our null hypothesis was that P equaled 0.02. And then our alternative hypothesis is that P is greater than the 0.02. Okay, so let's explain what it would mean to make a type 1 error for this example. So remember, we just talked about it. A type 1 error would be if the null hypothesis is true, but we reject it anyway. So for our example, we would make a type 1 error if the sample evidence led us to believe that P was actually greater than 0.02. Therefore, we would reject the null hypothesis, when in actuality, the proportion of children who experience headaches is not actually greater than or different from 0.02. So what would it look like to make a type 2 error? So remember, that's when the alternative hypothesis is true, but we still don't reject the null hypothesis. So in this case, if the researcher doesn't reject the null hypothesis, that the proportion of children experience headaches is equal to 0.02, when in actuality, that proportion is greater than 0.02. So another way to say that is that the sample evidence actually led the researcher to believe that P equaled 0.02 when the true proportion is greater than that. Okay, so these are just examples with the values in there of the type 1 and type 2 errors. Now the probability of making type 1 or type 2 errors, alpha, is going to be our Greek letter for the probability of making a type 1 error, and then beta is going to be our probability of making a type 2 error. So you can actually break these down. The probability of making a type 1 error is equal to the probability of rejecting the null hypothesis when it's actually true. And the probability of making a type 2 error would be equal to the probability of not rejecting the null hypothesis, even though the alternative hypothesis was true. Okay, so the level of significance is actually alpha, and it's the probability of making a type 1 error. So as the probability of a type 1 error increases, the probability of a type 2 error actually decreases, and vice versa. So as alpha increases, beta decreases, and the opposite is also true. So next, let's state some conclusions to hypothesis tests. So quick caution, we never accept the null hypothesis because without having access to the entire population, which is difficult for most situations, we don't know the exact value of the parameter stated in the null hypothesis. So rather what we do is we say we do not reject the null hypothesis. This is just like our court system. We actually never declare a defendant innocent, but rather we say they're not guilty. So example, same situation with the pharmaceutical company and 2% of the children having headaches as a side effect. The researcher still believes that the new antibiotic produces more than 2% of the people having headaches. And so we know the whole null hypothesis was P equaled 0.02. The alternative hypothesis was P is greater than 0.02. And so let's suppose the sample evidence indicates that A, the null hypothesis is rejected. So we're stating the conclusion. So the statement in the alternative hypothesis is that the proportion of children taking the new antibiotic who experience a headache as a side effect is more than 0.02. Because the null hypothesis equals 0.02 and it's rejected, that means there's sufficient evidence to conclude that the proportion of children who experience headaches as a side effect is more than 0.02. So just so you're aware, if you're getting a little lost here, we're just giving background on how to deal with the hypothesis testing and the null and alternative hypothesis. We didn't actually do anything with the data itself. We're just talking about what our conclusions would be. So now suppose that the sample evidence indicates that the null hypothesis was not rejected. What would that conclusion look like? Because the null hypothesis was not rejected, that would mean that there was not sufficient evidence to say that the proportion of children who experience headaches as a side effect is more than 0.02. Okay, so that's it for this one. It's just background on hypothesis testing and just the language that you're going to come across while you're working with hypothesis testing. All right, thanks for watching.